Welcome back to my class on statistical mechanics. We have been dealing with the canonical ensemble. In my first class, I dealt with the idea of formulation of the theory behind canonical ensemble. We obtained the partition function, and we also obtained the bridging equation between the micro world and the macro world, and that equation was A is equal to minus kt log q, where q was the partition function given by sum over all e raised to minus sum over all the states e raised to minus beta ei, where ei represents each state and I represents all the available states for the system. Now, from that partition function you can obtain the Helmholtz free energy, and now we are going to find out how from the Helmholtz free energy we will get all other thermodynamic quantities. There are a large number of other thermodynamic quantities like pressure, entropy, chemical potential, etc. We can find out from the first law of thermodynamics. We will be able to find out other thermodynamic quantities. We will see how we are going to get that. A equal to minus kt log qn, where qn represents the partition function for n particles. Now, from A we are going to obtain all other thermodynamic quantities. A is the Helmholtz free energy, and it is given by, from thermodynamics we know that A is equal to U minus Ts. Now, you can differentiate this expression A, therefore du, and the Ts you can differentiate. Taking the negative sign outside, you will get minus Tds minus Std. In that you have to substitute Tds is equal to du plus Pdv minus mu dn. Your first law of thermodynamics says that Tds is equal to du plus Pdv minus mu dn. You can substitute that in your equation for dA, and then you will be able to get dA is equal to minus Pdv plus mu dn minus S dt. That is, A is equal to U minus Ts. Differentiating, dA is equal to du minus Tds minus S dt. Now, first law of thermodynamics says that delta Q is equal to du plus delta W. First law of thermodynamics says that delta Q is equal to dE. In the earlier case, we used expression for energy as E. Now, we will be using U, du plus delta W, and that can be changed as delta Q by Clausius entropy equation Tds du plus delta W. Delta W can be any type of work, Pdv minus mu dn. Pdv is the mechanical work or the work done to increase the volume, and mu dn is the work done to remove the particles from the system. Therefore, Tds is equal to du plus Pdv minus mu dn, and this I will substitute here. Therefore, my dA now becomes du minus du plus Pdv minus mu dn minus S dt. Therefore, this du and minus du cancels. You will be getting this as minus Pdv plus mu dn minus S dt. Therefore, you can use this final expression. And then you can find all other thermodynamic quantities. Therefore, using this dA is equal to minus Pdv plus mu dn minus S dt. Now, using the partial derivative technique, you can keep your number and the temperature constant. Therefore, P will be equal to minus dou A by dou B, provided A is known. A is known from minus kt log q. Therefore, from if A is substituted here, you can obtain the pressure. Similarly, U can be obtained by taking partial derivative of A with respect to n, keeping volume and temperature constant. And entropy you can obtain from dou A by dou T, keeping V and n constants. Therefore, S is equal to minus dou A by dou T, keeping N and V as constants. Mu is equal to minus dou A by dou N, keeping V and T as constants. Therefore, S is equal to minus dou A by dou T. One of the most important equation is, which is not given here. We have obtained the equation for pressure, we have obtained the equation for chemical potential, we obtained the equation for entropy. Now, one of the most important equation is the equation for internal energy, that is not here. Therefore, we have to find out what is that equation for the internal energy. I will first show you that equation. You have this, then we will work out. A is equal to U minus Ts, rearranging U is equal to A plus Ts. But earlier I had shown you that S is equal to minus dou A by dou T. Therefore, I can substitute that S there. Therefore, U becomes A minus T dou A by dou T. A minus that is minus T dou A by dou T. U is equal to A minus T dou A by dou T. Now, we have to find some expression in such a way that matches with this U. That matches from starting from A, we have to find an expression for U that matches with this expression. For that, we have to take not the direct, it is not a direct method, we have to take the partial derivative of A by T. A is a function of temperature. Therefore, first you take the derivative A by T. A by T means A T raised to minus 1 you can take. 1 by T, keeping 1 by T as constant, you can have the derivative of A with respect to T, then dou A by dou T, plus A I will be keeping as constant, then I will be taking derivative of 1 by T with respect to T, which I will be getting that as minus A by T square. 1 by T dou A by dou T minus A by T square. Now, I will multiply this throughout by T minus T square. Therefore, minus T square dou A by dou T of A by T minus T square dou by dou T of A by T. Now, when I multiply with the minus T square, 1 T and 1 T cancels, I will get minus T dou A by dou T, and then minus T square I multiply, this negative sign becomes plus A. Therefore, A I can write first and then minus T dou A by dou T on the second, and this is nothing but your earlier equation U. Therefore, what you got is now A minus T dou A by dou T. A minus T dou A by dou T is U. Therefore, minus T square dou by dou T of A by T is U. Dou by dou T of A by T is U. But A is equal to minus K T log Q. Minus K T log Q. Therefore, I can substitute that A is equal to minus K T log Q. Therefore, I have this T and T cancel, minus sign comes outside. Therefore, it becomes plus K I can take outside. T square is already there. Therefore, K T square dou by dou T of log Q n. This is the expression for internal energy. Therefore, I will tell you once again what I had done. Initially, what I did is I took my U is equal to A plus T s. Then S I substituted as minus dou A by dou T. Therefore, I will be getting my equation as A minus T dou A by dou T. And in order to get this A minus T dou A by dou T, what I did is I took dou by dou T of A by T, which on differentiating I will get minus 1 by T dou A by dou T minus A by T square. Multiplying throughout by minus T square, I will be able to get this minus T square dou by dou T of A by T is equal to A minus T dou A by dou T, which is nothing but U. Therefore, U is equal to minus T square. U is equal to minus T square dou by dou T of A by T, but A is equal to minus K T log Q. Therefore, that minus and minus sign cancels, 1 T and 1 T cancels, K I can take outside. Therefore, it becomes K T square dou by dou T of log Q n. Similarly, you obtained this expression as K T square dou by dou T of log Q n. Now, that is U is equal to K T square dou by dou T of log Q n. Dou by dou T of log Q n. I am giving a different expression for this. This can be rewritten in this form. U is equal to minus dou by dou beta of log Q n, where dou beta is 1 by K T. how you are getting, whether from this you will be able to get this expression. Beta is 1 by kT, therefore minus of dou by 1 by kT log Qn, log Qn. This I can write it as K, I can take to the numerator, therefore this becomes minus K dou by dou of 1 by T log Qn, 1 by T log Qn, which dou of 1 by T will be equal to minus 1 by T square dou T. Therefore, this expression becomes minus K dou of 1 by T square dou T of log Qn, minus 1 by T square dou by dou T of log Qn. Then minus minus cancels, T square goes to the numerator, which I will get it as Kt square dou by dou beta of, sorry, yes, dou by dou T of log Qn, dou by dou T of log Qn. That is, this equation Kt square dou by dou T of log Qn and minus dou by dou beta of log Qn are same. Why you have two different equations? Sometimes your energy, this partition function may be expressing in the form, may be expressed in the form of beta. For example, the partition function for a harmonic oscillator, later you will see that it is equal to 1 by beta h cut omega. Therefore, it is very easy. If you want to find the internal energy, you can directly differentiate with respect to beta and immediately obtain what is the internal energy. Sometimes your partition function will be expressed in the form of temperature. For example, partition function for an ideal gas is equal to V by lambda cube, where lambda cube is equal to h cube divided by 2 pi m kT whole raised to 3 by 2. In that case, lambda cube is not there now, T is there. Your partition function appears in the form of T. Then you can use this formula. Therefore, now you have two formulas are there. One formula is minus dou by dou beta of log Qn, and the second formula is Kt square dou by dou T of log Qn. Therefore, these two equations, with these two equations, you will be able to obtain the internal energy. Now, we will go for some problems. Therefore, let us rewind what we had studied. From your partition function, I told you that you will be able to obtain the Helmholtz free energy, and earlier case your whole thermodynamics in microcanonical ensemble you got from entropy. Here your whole thermodynamics you will get from Helmholtz free energy. Helmholtz free energy, and the equations are: pressure is equal to minus dou A by dou B, entropy is equal to minus dou A by dou T, chemical potential is equal to plus dou A by dou N, and in the case of internal energy, Kt square dou by dou T of log Qn, that log Qn you can express again in terms of Helmholtz free energy, or minus dou by dou beta of log Qn. Therefore, it is guaranteed that if you find the partition function, from the partition function you can obtain your Helmholtz free energy, and from Helmholtz free energy you will be able to get all the thermodynamic quantities. So, let us find a typical problem that is given in one of the competitive examination. The free energy of a gas of n particles in a volume V and at a temperature T is given by, the equation appears to be a very big equation. A is equal to minus n kT log A0 V Kb. Kb means Boltzmann constant, the T whole raised to 5 by 2, then n is there, where A0 is a constant and Kb denotes the Boltzmann constant. What is the internal energy of the gas? You are asked to find what is the internal energy of the gas. First of all, I will give you that directly give you the partition function. You can write your partition. First of all, you have to use the concept of partition function. Therefore, let us do this problem. You are given A is equal to minus nkt logarithm of something into T. You are only asked to find out what is the internal energy. Therefore, your internal energy U is equal to, now I will use this expression in terms of T. Therefore, Kt square dou by dou T of log Qn, dou by dou T of log Qn. You are given A is equal to minus nkt log some constants were there and t raised to all other things you can put it as constants. This was your expression. A is equal to minus nkt log c t raised to 5 by 2. This was your expression. And you can say that this expression I can write it as, rewrite this expression as minus kt log c t. C I can take it as a constant. C I can take this raised to n, t 5n divided by 2, because y log x I can write it as log x raised to y, log s raised to y. I have taken that n as the exponent of this c and t, c raised to n, t raised to 5 by 2. Now, if you compare this with your minus kt log qn, your qn is now some constant, I will call it as c prime, c raised to n I will call it as t prime, c prime, t raised to 5n by 2. Therefore, my partition function is nothing but t c prime t 5 t raised to 5 by 2n. Therefore, that I can substitute here, and logarithm of this one, logarithm of log q, logarithm of a b, I can write it as log a plus log b, log a and log b. Therefore, log qn, when I substitute this there, this equation now becomes kt square dou by dou t of logarithm of c prime t raised to 5 by 2, 5n by 2, sorry, 5n divided by 2. Now, when I take the partial derivative means only that function can be taken derivative, all other things will be constants. Therefore, when I take this log c prime and t raised to 5 by 2, I can split this into log c prime plus log t 5n by 2. When I substitute that, automatically the first part, since it is a constant, it will disappear. It will not be there. Therefore, this expression simply changes to only you are required to take the derivative of dou by dou t of log t raised to 5n divided by 2, kt square log t raised to 5n by 2, and logarithm of t raised to 5n by 2 by using this expression log x raised to y, you can write that as y log x. Therefore, it becomes 5n by 2 log t, 5n by 2 log t. Therefore, 5n by 2 I can take outside, I will write here. Therefore, I have this kt square 5n by 2, and I have to take only the partial derivative of log t with respect to t, log t with respect to t, which I will be getting that as 1 by t. Therefore, this t and this t cancels, I will be getting my internal energy as 5 by 2 nkt, 5 by 2 nkt. Therefore, the thing that you have to remember is your partition function or your partition function may contain any different types of variables may be there in your partition function, but all your expressions like pressure, your pressure was minus dou A by dou V, keeping V and keeping n and t as constants. Therefore, in your partition function, if you have that partition function contains n and t, they will be acting as constants, only derivative will be with respect to p. Therefore, all other quantities, if your partition function, if it is q, if I say that v raised to n, some e raised to n, what happens is that if you are taking the derivative with respect to b, what we need to find out is, if I take this log q, you can say this expression is VE whole raised to n, VE whole raised to n. Therefore, if I take log q, this will become n log VE, n log VE, n log VE, or you can say this is some, instead of E you can have U also. If you are taking the partial derivative only with respect to V, all other things will be constant. All other things will be constant. Therefore, there is no need to take the partial derivative of E. This is how you can solve it. Therefore, you are given Helmholtz-free energy. Sometimes you will be given directly the partition function, or sometimes you will be given A, and then if A is given to you, you have to rewrite that in the form of minus kT log Qn and find out what is log Qn, or if only in the case of internal energy. Otherwise, you can directly take the partial derivative and find the thermodynamic quantities. Therefore, this is the way in which from thermodynamics you have the equations that you have is pressure is equal to minus dou A by dou V, then S is equal to minus dou A by dou T, chemical potential is equal to minus dou A by dou N, and your internal energy, you can have two expressions. One is equal to kT square dou by dou T of log Qn, and U is equal to minus dou by dou beta of log Qn. Therefore, directly if the partition function is known, you are sure to get all the thermodynamic quantities. We will go for one more problem. This is how I had done that. Q is equal to C T 5n by 2, and then substitute it in that problem. Yes. Now, we will go for the second problem. Consider a two-level quantum system with energies E1 equal to 0 and E2 is equal to, or epsilon 2 is equal to epsilon. Now, what is the Helmholtz free energy of the system? You are given first energy level is 0 and the second energy level is epsilon. You are asked to find out what is the Helmholtz free energy. Therefore, here you are asked to find out what is the Helmholtz free energy, which is given by minus kT log Q. Therefore, here you have to find out what is the partition function, and then you will have to substitute. Therefore, what is the partition function? Sum of all the energy levels, e raised to minus beta I, Ei. Therefore, I. Therefore, first energy level is given to be 0 and the second energy level is given to be epsilon. Therefore, first energy level e raised to 0 means 1, 1 plus e raised to minus beta epsilon is your Q. Therefore, A will be equal to minus kT log 1 plus e raised to minus beta epsilon. You will be able to get this as minus kT log 1 plus e raised to minus beta epsilon. Therefore, this is the answer, minus kT log 1 plus e raised to minus beta epsilon. You have been listening to the method of finding the thermodynamics of canonical ensemble. I had given you the equations of finding the thermodynamics using the first law of thermodynamics, and from your partition function, in this method what I had given you is that from the partition function you can calculate Helmholtz free energy, and from Helmholtz free energy you will be able to get all the thermodynamics. I hope you have been you are clear about all these things, and now I wind up. Thank you.